Everybody welcome Fred Sloop.
Thank you, John.
Okay, you're welcome.
Okay. We're going to go back almost a year ago. There was quite a bit of excitement here in planet Earth. But of course the astronomical community was in a tizzy because we were going to have a close encounter with an asteroid. It's 2012 DA-14. It was discovered by the Spaniards, and they named it Duende, which is elf. The interesting thing about this was that this asteroid, about 30 meters in diameter, was going to have a close pass of the Earth. So close, in fact, that it was going to fly closer to the Earth than the orbital area of our geosynchronous satellites. So it was a big deal. A lot of people were excited, and of course backyard astronomers were going to be able to watch this thing as it rapidly transitioned across the sky. The thing of note is that this is from a NASA page here. It says, there is no chance that the asteroid might be on collision course with Earth. So, we kind of keep that in mind as we move on in time here. Next slide, please. Next slide. Okay. That drawing up in there, that was the approximate size of it relative to the space shuttle. Let's go to the next slide, please. This was my favorite piece of artwork to show you the relative size of ELF. A nice thing to do is just position it hovering above a football field. Okay, next slide, please. NASA put out, on a website this map that would show this close pass. It had the times and so on. NASA TV is up and running. There's a lot of excitement. Next slide. We've got some spacing issues here. This is crossing platforms and crossing different versions of Microsoft Office, PowerPoint, but you get the gist of it anyway. 16 hours prior to this close encounter with 2012 DA-14, a brilliant fireball appeared in the sky over Chelyabinsk, Russia. Aaron, can you go ahead and run that OGV movie here? Dash cams are wonderful things. And of course, they're all the rage in Russia because of the issues with insurance.
Yep.
Mm.
What you saw in that video was an asteroid 19 meters in diameter, transitioning across 250 kilometers, moving at approximately Mach 60.
Mm-hmm.
Okay. Next slide, please. Next slide. Okay, this simply shows the location. First of all, the arrow is the direction. This thing came out of sunrise, so it came from the direction of the sun. This thing actually has a pointer here. I'm going to turn my back to everybody and just use it. Now here's what's left of the Aral Sea, and here's Novaya Zemlya, so it kind of lies in between Moscow. It's up here. So you get an idea of where this is located. Next slide. And you can see this object is a small asteroid. It has a very shallow entry angle, only 18 degrees. That's why it transitions across so much of the sky. It said it was moving at Mach 60. That's 19 kilometers per second. And the entry mass initially was calculated to be between 1.2 and 1.3 million kilograms, 12 to 13,000 metric tons. And when you look at the energy that is involved in an object that big and moving that fast, we're talking about somewhere in the neighborhood of 500 to 600 kilotons of potential energy. This just is to show you the relative size of the object. You see a naval cruiser at the top, a Boeing aircraft 747. Right behind the 747 is the artist's version of this Chelyabinsk object. Behind it, that's the big iron meteor that formed the Barringer crater in Arizona. And that big thing down at the bottom, that's the hypothesized size and composition of the Tunguska object. Okay. This object fragmented and underwent a series of catastrophic airbursts. In actuality, the object was moving so fast and these explosions occurred in such rapid succession, it was a matter of, say, 2 seconds. And there were dozens of very energetic outbursts. And so it appears like only about 2 or 3, but in fact it was probably well in excess of 20. It produced a shock wave. That kind of looks like, that pattern there kind of reminds me of a Romulan bird of prey. Those of you that are Star Trek fans. If you notice, the energy, that's the energy as it was imparted to the ground, is actually perpendicular to the flight of the body. And there's rational physical reasons for that. You got to consider that in the front of this object there's an incredible pressure wave that's well, I know when the final object in this mass was crushed, when it detonated, the pressure in the wave was about 2,600 psi, about 18 megapascal. Those of you that like bar, that's 180 bar. And that pressure wave, as it swept out across the countryside, damaged approximately 7,200 buildings. I should also state, keep in mind, that this pressure wave was not really directed at the ground because of the angle of the trajectory, and because of the sequential nature of the explosions. It was projected cylindrically, but in 360-degree direction. So this could have been much worse. We'll talk about it here in a little bit, with a little difference in the composition of the asteroid and a little different angle. An awful lot more energy could have been directed at the ground. You put the term catastrophic in there. That's not really good. It should have said serious. Some of the damage was serious, and of course that was the most notable one was the Chelyabinsk zinc plant. And you see there's actually a photograph there on the left that shows the plant at the moment of when the roof collapsed down into the building. Most of the damage, though, simply involved broken windows, pulled down suspended ceilings, and then caved-in garage doors. And that's just a series of photos there that shows apartment buildings, storefronts, inside of a public building, inside of a school up there in the upper left corner. And just more of the same. The number of injured numbered more than 1,500. Most of the injuries were lacerations, and that was from people basically standing in front of their windows, looking out after the light of that object passing drew their attention to the outside, not knowing depending on how far away they were, anywhere from 1 to 3 minutes would come the shock waves, and they were pretty considerable. There were a couple of, I think it was only 2 or so, maybe 2 to 5 people that actually required an extended hospital stay. That's because they were blown off their feet. They were much closer to the object than most of the others. Most of the injuries, a lot of the injuries occurred in the big population centers. Chelyabinsk was one, but you know it was I think about 28 kilometers away from the path of this object. Of course, press coverage was pretty exciting. I stuck that one in there in the bottom just to give it a little balance here. You know, that's one of the supermarket tabloids. Anytime anything falls from the sky, it's got to be a UFO or the late president of the Teamsters, Jimmy Hoffa. It's one of the two. It's usually one of those two. Okay. This was visually the most recorded event of its type in history. You know, an incredible amount of video, of course, that came mostly the courtesy of the dash cams in cars, but there are also quite a few security cameras that got some pretty clear images. And then there was actually some still photography taken. The photo in the upper right, that's not a screen capture from a video. That is an actual still photo. A photographer was out shooting pictures in the early morning at a lake and had the presence of mind to snap that particular photograph. More pictures, both with the fireball coming across the sky, and then the contrail that you see there. That's a mixture of vaporized rock, and dust. There were approximately 2,800 metric tons of dust, it's theorized, that were yielded from the breakup of this body. Some of the pictures were pretty pretty attractive. This was the nicest one that I found. You notice the contrail is thicker in some areas than others. There's that segment there, and that's where a series of detonations occurred in very rapid succession. That is that thick area of the contrail there. That's probably 40 kilometers or more in length, and of course this body actually crossed that distance in about 2 seconds. Okay, there was an enormous amount of other data that was available as well. Some of it is not available all the time, and that is the data from the defense satellites. But there was seismic data, infrasound data, and then two basic different types of satellites: the meteorological satellites, and then the defense satellites. The defense satellite data is absolutely critical, and has been critical in trying to get a handle on just how common these types of events are. I mean, consider that 70% of the Earth is covered by ocean, and so you would just make the leap of faith here that about 70% of these sorts of events would occur over water, and quite possibly people wouldn't be around to see them or hear them. We're going to flesh this out a little bit more towards the end of this talk, because having access to a full suite of data really has broadened the understanding by the scientific community of such occurrences, and they're actually so common now that there is a concern, and we'll talk about that a little bit later. There's a concern from a safety standpoint, especially as world population grows, people scatter more and more across the across the globe. By the way, that picture at the bottom, that's an infrasound station. That particular one is in Greenland. Infrasound, think of it as just like a big radio receiver. But it's looking at very, very low frequency pressure waves that occur in the atmosphere. Those are set up for defense purposes. It has to do with the International Monitoring Program for nuclear weapons. This map, I just tossed that up there to show the numerous sites that are involved in this international monitoring system. This, of course, is the nuclear test ban treaty enforcement here by setting these stations up. Now, in addition to them, the United States has its own system. And you can see that the U.S. basically has more infrasound stations in the continental U.S. than the rest of the world has combined. And also mentioned before that data was made available from both meteorological and defense satellites. And that includes data such as visible, infrared, ultraviolet, multispectral instrumentation that can give a lot of information on events that occur above the Earth and on the Earth. Of course, this cumulative amount of data made for some great science opportunities, and I just popped up a couple of journal covers there. Most notable one is the one on the left, and that's the journal Nature. A couple of months ago, Nature had two absolutely awesome articles on this, and I would recommend that anyone that would have any interest in this event go to that magazine. Go to the library if you don't have access to it otherwise. But there's two excellent articles. Okay, when we're looking at the scientific data, the first thing that I've popped up here are light curves. Light curves are very important when it comes to our defense satellites. Initially, our DSP satellites just had infrared sensors on, but then they got into a multispectral range, and it allows them to not only gather more data, but also from that data come up with more meaningful conclusions as to a given event. From the light curves that you see there, the total light that was irradiated from this event was equivalent to 90 kilotons. That's just light. That's the mostly the visible light and the UV component, but mostly visible. How much energy is that? 90 kilotons, that's 6 Nagasaki bombs. That's a lot of energy, and that's just in the light spectrum. Now they have equations then that they plug that light output into, and that's how the defense satellite system came up with the total energy that was evolved from the destruction of this body as being about 590 kilotons. That brightness peak.
Sorry, I was trying to...
Where would you go here? Okay. That brightness peak occurred at 9:20 and 32.2 seconds in the morning local time. The astronomical brightness was minus 28. And that particular reading was in the Silicon bandpass. And so when you would translate that into what a person would experience with their own eye, it was a brightness that was about 30 times brighter than the sun. There were people that actually did suffer momentary blindness, eye pain. There was some occurrence, a few score to maybe a few hundred, individuals that actually got sunburned. We'll use the term, with little quote marks around here, sunburned, but that, the UV flux was pretty considerable with this as well. Okay, when we go to the infrasound, we're looking at anywhere from 0.01 to 4 hertz. So when we talk about low frequency, we're talking about low frequency and extraordinarily long wavelengths. Most of their useful data, by the way, is less than 1 hertz. This was, as far as the international monitoring stations of the UN were concerned, there were 17 that actually picked up this event. I think the one that was the furthest away was in Antarctica. And the infrasound pressure wave actually was detected multiple times. So this thing was propagating around and around the globe multiple times. I know it was picked up at least twice by most stations. That little globe over there, that just shows you DF cut, what I call DF cuts, and from the stations, and kind of it's a reciprocal bearing, and trying to locate where this event occurred. And you can see it's clustered in on an area there that to me looks like a couple 100,000 square miles, but there's quite a close agreement with a number of the stations to actually detect exactly where this thing occurred. This, by the way, was the largest infrasound event that this network had ever picked up. Now, when you take the infrasound, the government satellites using the light sensor, seismic data, and other systems, you can see in the column right there in the middle, that's the best estimate for energy yield from this event. And you can see it goes from a low estimate of 430 to a high estimate of 600. So, generally they just say, well, this was about a 500 kiloton or half megaton energy yielding event. Now, from the dash cam and security camera data, I was really surprised at the quality of the data that you can pull out of these cameras. You can see, if you look hard, especially on the right side in the middle panel, you're actually, by using filters to darken the background, you can actually pick out probably more than a dozen individual objects. See, as this thing came in, it began to break up, and it broke up in some sort of a sequence in that before the body was essentially obliterated, there were 20 separate, we'll call them boulders. 21. There were 21. There were 20 that were about 10,000, approximately on average, 10,000 kilograms each. And then a big one up at the front that was 20 or 30,000 kilograms. Just some bullets there to point out that the body broke up for the most part between, most of the breakup occurred between 45 kilometers in altitude and 30. The total number of boulders was 21. As I mentioned before, 20 at about 10,000 kilograms, the larger lead boulder of about 20,000. The smaller boulders disintegrated between 26 and 24 kilometers in altitude. The pressure from the pressure wave, a shock wave as it's pushing into the atmosphere, was probably somewhere between 10 and 13 megapascals. So it'd be 130 bar. And then the lead boulder was catastrophically destroyed. That was the last hurrah for this object at about 22 kilometers above the surface. This, it's kind of there's a lot of information in this, but the big thing is, when you look at that thing, it kind of looks like mountains. That is the light curve. And when you look across the bottom, you see those bars that stick up. What those are acoustic signals. And the acoustic signals are individual objects either breaking up or being obliterated. We're going to try a video here. Can go ahead and...
Are you ready?
And this is the live leak. Yeah. Now turn it up.
That's what I'm doing.
Those are all detonations.
Where did the data come from?
Pardon me?
Where did the sound data come from?
Oh, it came off of these videos.
Ah.
The heck out of the camera's mine. Like, I'm hitting peak here. Hitting at the peak here. Just
Okay,
just
now-
dynamic range for it to be.
Yeah, now we're good.
Yeah.
Okay, now you know, people are too accustomed to movies, to where you see something and you hear the sound at the same time, including, of course, weapons fire in space. But the fact of the matter is this thing was traveling at Mach 60, and these events occurred, you know, at that speed, at that hypersonic speed. Unfortunately, sound does not cooperate. You know, what is the speed of sound? Is like, what, 300 meters per second? And you've got this object that's moving at 19 kilometers per second. So, I don't know what the delay was or the distance. It looked to me like this video was shot fairly close, probably not more than maybe 25 kilometers away from where this body passed. Anyway, I actually get a big kick out of that thing. It tells you an awful lot about what occurred with this body, how it broke up, and how the individual pieces were destroyed due to the high pressure circumstance that they were in. Now, one fragment, one of those detonations, threw a fragment out of the main debris train. Virtually everything that was in that main train was destroyed. That one fragment, which is indicated there as F1, was actually, it got a little English to it, and it was kicked out of that main debris stream. And it is that body then that, you know, once it was kicked out, it got out of that high pressure wave of all that debris as it was pushing down into the atmosphere. That's the thing that survived. And actually, of course, it ablated quite a bit because it was still quite hot. I should mention that the temperature around this body as it was passing through the atmosphere was something on the order of 5,000 to 7,000 degrees centigrade. So that is why approximately 76% of this body was disintegrated. It was vaporized. That's where what was left of F1 popped through the ice on the lake that is southeast of Chelyabinsk. There was a limited strewn field, which is, of course, the debris field, the meteorite field from the breakup of this object. You notice what I've written down there is that only 0.03 to 0.05% of the original mass of this thing actually were fragments that made it to the ground. That was about 6,000 kilograms out of an original mass of 13 million. That fellow is holding, I think, about the second largest fragment that was found in his hand. And then you see off to the upper left there piles of smaller meteorites that were picked up along that line that's in the map on the bottom. That is what was fished out of the lake, and that was a couple of months after this occurred. I guess the divers must have waited until most of the ice melted before they went down. It's about 600 kilograms.
It's not easy to get out.
And by the way, when they managed to get that thing up intact, and then when they set it on a scale, it broke.
Oh.
It actually fractured into 3 pieces.
Oh.
So, a little harsh treatment to a really fine specimen. However, you can buy them on eBay. Early on, I checked the prices here about a month or so ago, and you can get one about the size of your little fingernail. That's a 3 dimension for I guess about $70. Bigger ones, I've actually seen ones like the size of a walnut, and they're asking $1,200, $1,400 for them. They will be available soon enough at lower prices because people get excited, they want to buy the things, but hopefully there'll be more in the market than the initial excitement will buy up, and that's when people like me can go in and get them for half price. Nearly 24% of that original body was converted to dust of various sizes. Recovery of the meteorites, of those fragments, and the dust have provided some great insight into the type of body that this was, its chemical composition, and also why it was destroyed in the manner that it was. One thing the people of the Chelyabinsk Oblast in Russia can be thankful for is that this object was highly fractured. It literally had, I would assume, hundreds of thousands to millions of fractures, small fractures, that pervaded throughout the entire mass. I don't know if you can see the detail in the larger object on the left, but there's just like a whole series of fine little lines that go through that. Those are all fractures. And the fractures, by the way, are filled, for the most part, with metal. The fracturing was enough that it heated up the body through the compression to where some of the metal that was in it melted. and filled in those voids. But those are all areas of great weakness as far as the body was concerned. Had that, and this probably occurred due to a collision with another body in space sometime in the distant past. If it didn't have those fractures, chances are it would have stayed more intact lower down into the atmosphere. And then rather than have like a line charge go off over a distance of tens of kilometers, you would have had a point source explosion. And chances are that the energy imparted to the ground would have been something that the locals would not want to have had to deal with. We're talking about the types of energy that would have knocked down buildings, kind of a Tunguska sort of thing, on a smaller scale, though, of course. Okay. Oh, also, you can see on the right, there's two panels there. The electron photomicrograph. This plus the elemental analysis that they put this thing through allowed them to type this. It's a chondrule containing stony meteorite. Has a low total iron and it has a low total metal. And when you put those things together, that makes this an ordinary chondrite. And in particular, this is an LL5. LL is a type of ordinary chondrite that's the low metal, the low iron, the low total metal, and it's group 5, which is all this is a taxonomic system for trying to pigeonhole these things so you can for grouping purposes and also for telling the difference between one body and another. Anyway, this body has gone through a certain degree of thermal metamorphism, which would be probably 500 degrees C at the highest, but for some period of time. And when you look at the various the chemical composition and ratios of one thing to another, like the change in a certain oxygen isotope with the concentration of iron oxide, or the iron to magnesium ratio versus the iron to silica, or the concentrations of the various rare earth elements in it, it makes it an LL chondrite. I don't know if you can see in the lower right corner, that chart has just a series of circles and ellipses on it, and that's groupings, what I call taxonomic groupings for the meteorites. And you notice the Chelyabinsk one right in the middle towards the bottom, and it sits inside the LL ellipse. Okay, the satellite and ground-based photographic and video data permitted reconstruction of the trajectory of this body through the atmosphere. And then, of course, they took that trajectory and they just worked it outwards. And so that allowed them to come up with its orbit prior to entry into the atmosphere. That's the final approach. That red vector there is the final approach of the Chelyabinsk body to the Earth. The green line in that top chart that's off to the left, that was the orbit of the asteroid at ELF that everyone was looking forward to seeing. Until, of course, the unexpected arrival of the Chelyabinsk body. And then they were able to reconstruct the orbit of this impactor, its entire orbit. And you see it's kind of an offset thing. The furthest distance takes it right out into the main asteroid belt. And on its closest approach to the Sun, it's in right close to the orbit of Venus. Actually, was. Now, those orbital parameters, along with the compositional analysis that was done, allowed made it possible to associate this boulder that came into the atmosphere at Chelyabinsk with asteroid 86039, also known as 1999 NC43. This asteroid, pretty sizable, 2.2 kilometers in length, has a very stable and well-known orbit. I looked up here recently like when its next close encounter is with Earth, and it's going to pass, I think, like within 1 million miles of Earth, but it's like the year 2173. So this, even though it's a near-Earth asteroid, it's not one to worry about currently. Regardless, this body, it is hypothesized, is where the Chelyabinsk object came from. Probably some minor collision that ejected the body out from the well-established orbit of its parent. And this is it's nothing that really has any great effect. It won't have an effect because it's so tenuous. But well, at least temporarily, there was a new stratospheric dust belt that came about due to this object. And you can see in the series of photos on the left, you can see the original contrail, and then you notice as you get down, if you go diagonally, that's the fourth image in the series, how it's being drawn out and distributed. It existed for quite a few months. I don't know what's left of it. It has been dissipating ever since it was first formed. But it existed just above the Jung layer in the stratosphere. That's the layer, where the sulfate layer in the atmosphere. So it existed above there. If you look at the series of plots on the right, you notice the big set of lines in the lower part along the x-axis. That's optical readings from the Jung layer. That small bulge above, that's that new dust layer. At its maximum, its vertical depth was about 5 kilometers, about 300 to 400 kilometers wide, and it actually spanned the entire northern latitude of the planet. Okay. This event has encouraged people in science, to look more in depth at the frequency and the hazard of small impactors. You probably are well aware of the fact that we do get a little freaked out over the presence of large near-Earth asteroids, especially ones that are Earth crossers, because at least once and maybe a couple of other times we've had mass extinctions that have resulted due to close encounters with these things when they decide to impact the Earth. Think Chicxulub at the end of the Cretaceous period. But we've not really paid a lot of attention to smaller ones. We actually have active programs where we're doing sky surveys every single night to locate, identify, and establish the orbits of larger objects. But there are people now that are saying maybe you should be looking at smaller ones as well. I don't know if you can read anything in that chart that I made up. That was just a sampling of meteor airbursts that have been known over time. Let's see. The very first one, that's 1908. I didn't take any from before 1908. I only took ones from the 20th century and beyond. And I didn't even take all those and put in this thing. Notice the first one is look at the second one there, that's the one that occurred in Amazonia. A lot of people are unaware of that thing. The artist illustration in the lower right is ostensibly the passage of that body into the atmosphere. The one in the middle, by the way, that's a postage stamp that the Soviet Union put out, and that's for the Chelyabinsk fall that occurred in 1947 in the Chelyabinsk mountains in Russia. I actually got a couple of fragments of that and had a jeweler make it into necklaces for my daughters for Christmas or something one year. Regardless, this event and then the opening up of data from the defense satellites and also from the international monitoring stations that look after the nuclear test ban treaty has shown that these events occur more often than most people would think of. And of course, with a world where we're spreading out more and more people, more towns, more cities, there's going to be more opportunity for people to be affected by bodies that come into the atmosphere. Not only the ones that are going to impact the ground, but these airbursts are pretty dangerous. Let's think Tunguska. Of course, NASA has this growing all-sky network. We have 12 stations here in the United States now. And this is just one night. And this is, fireballs. And a lot of these are not, bigger than, peas, or some might be the size of walnuts. This is one night. It was January 3rd, just not 2 weeks ago. There were 27 fireballs seen in the area where these cameras are looking. And you see it's very, very small land area compared to just the United States, not to mention, the surface of the entire world. And so people that worry about these sorts of things feel that the nature of the threat is changing. What's the threat? The threat is the threat from outer space, right? From these bodies coming in and conceivably imparting some level of harm to people on the ground. We're starting to see, if you're looking at that ellipse that's in the middle, that's getting populated with more and more events as we have more and more data. They occur more frequently than was known prior to the opening up of a lot of these classified sources, previously classified sources. So this isn't, universal, but there are people that feel that low altitude airbursts are something that we should be really concerned about. And so what they're proposing is that we should up the ante as far as these programs are concerned. Where we're doing these surveillances, looking for large bodies. We need to be looking for smaller ones as well. How small? This suggestion here is down as small as 100 meters. And I just threw this slide in just to show you that depending on where the body is destroyed, has an awful lot, has a great effect with how bad things are going to be on the ground. The one on the left, that's Tunguska, or you could even take and say that's Chelyabinsk, where the body is destroyed some distance above the ground. You have a pressure wave that comes down. With Tunguska, there was enough radiant energy that you actually had trees scorched. The one on the right, that's an event that occurred about 28 million years ago. And that's the hypothesized source of Libyan glass. What is it? That's a body that detonated fairly close to the ground. The plasma, that 5, 6, 7,000 degree plasma, then coupled with the surface of the land there. I didn't put a picture in. I should have. I got some great aerial photographs of this. But you're looking at a land area. It's about the size of a city. And it's all fused glass. And you know, that kind of harkens back to the days of the Cold War. You remember the threats about how we were going to take and turn the enemy's land into a plane of glass? Well, that's what we're talking about here. An awful lot of heat and a lot of energy imparted to the ground surface. I have to throw in my customary picture of Tunguska just because I like it. Okay, I'm going to finish up here with the fact that Chelyabinsk was not the last airburst event. There have been several since. The last one was 2 weeks ago tomorrow. The body is 2014 AA. And on January, it was discovered just hours prior to its entry into the atmosphere. The sky, a photo on the left, you might be able to see the body. It's a little streak. It has a circle around it, kind of a magenta circle. Anyway, it was hypothesized then, once it was discovered, just hours before it entered the atmosphere. There's this map on the right that this is the area that it was thought that it would come into and either be destroyed in the air or impact the ground. And you look at the infrasound data on the right, and it shows that the body did indeed, it was indeed destroyed catastrophically in an airburst just northeast of French Guiana. This thing was very small, by the way. It was only about 3 meters in diameter. No threat to those of us down here in terra firma. And I'll leave you with something that's a little more upbeat. And thank you.